Well, good day, students. So here we have our next statistical test, the chi-square test of association. We're going to use this test when we want to test the association or examine the association or relationship between two categorical variables. This is a very popular statistic in biomedical research, epidemiological research, and just straight medical research as well. You can see, for example, here we have a classic study done on aspirin consumption. So a large number of men either consumed a placebo, like a sugar pill, or they consumed an aspirin. And then over time, the doctors tracked and recorded whether those men had suffered a recurrent fatal heart attack or if they did not have another heart attack. So you can see here 189 men consumed the sugar pill and had a heart attack. 10,845 consumed the sugar pill and did not have a heart attack, and then similar numbers for the aspirin. So are these two variables, having a heart attack or not, versus consuming the placebo or aspirin, are those two variables related in the population? That's the question we want to answer. So here's your typical handout. You want to save this or print it for your records. So we have our assumptions, the hypotheses, the chi-square distribution here, and the formulas on the second sheet. So let's go ahead and work through this particular example. So we'll plug and chug through and see what these genuine data tell us about the relationship between the aspirin consumption and the heart attack. So here I've rewritten the question: is there a population relationship between aspirin consumption and the recurrence of the heart attack? Now, based on knowledge of physio, many people believe that such a relationship might exist. So do these genuine data here from a large study support the hypothesis? Now, this table, by the way, is what's referred to as a contingency table. And notice for this particular example, we have 2 rows and 2 columns. So when I'm talking about number of rows and number of columns a little bit later, that's what we're referring to, this contingency table. Imagine another study where maybe we had an additional group of men who consumed vitamin C every day. That would then put another row here, and that would be a 3x2 contingency table. But this is a 2x2 contingency table, 2 rows, 2 columns. So let's work through the steps of NHST using an alpha level of 0.05. Now, it's also important to remember then that we are not estimating 2 population means like we have before. So we're not going to talk about population 1, population 2 here. Instead, we're going to talk about one population parameter, and that is the correlation between the 2 categorical variables. So our hypotheses then are written in that way. So the null hypothesis is that aspirin consumption is not correlated with heart attack recurrence in the population. Obviously, that needs to be a K there. And then in the alternative hypothesis, we have 2 different directions here. The aspirin consumption is correlated such that it reduces the incidence of the heart attack, and that's what we're expecting. Or it's the other way, the aspirin consumption actually increases the incidence of the heart attack. So following along on our worksheet then, we set up our chi-square distribution here. It's a one-tailed distribution because you can never get a negative chi-square. It's going to be a one-tailed test, even though the hypotheses are directional. To find the critical value, we need the degrees of freedom, and for the chi-square, it's number of rows in that table minus 1 times number of columns in that table minus 1. And so that is just simply 2 minus 1 times 2 minus 1. That gives us 1. That's 1 degree of freedom, alpha 0.5. So let's go to the table. So the table A7 here is the chi-square table, and 1 degree of freedom, alpha 0.5, 3.84. So that will be our chi-square critical value. So there's our 3.84. We next need to compute the expected cell frequencies, and these are the values that are expected under the assumption that the null hypothesis is true. Now I want you to round these numbers to 2 decimal places. Don't round to a whole number. Even though you cannot have a fraction of a person, these are theoretical numbers, so you want to keep at least 2 decimals when you compute your expected values. So you can see here what I've done is I've recopied the table, and then I have these numbers in parentheses. These are the expected frequencies. Now the first thing you want to do is get the row totals and the column totals. So 189 plus 10,845 gives me 11,034. 104 plus 10,0933 gives me 11,037. And you can see what they tried to do here was they tried to get about equal numbers of men consuming the placebo or the aspirin. So those numbers are about equal on purpose because the researchers designed the study that way. Then to get the column totals, 189 plus 104 gives me the 293. and then 10,084.5 plus 10,933 gives me 21778. Now if I add all four of these numbers up, I get 22071. Similarly, I can add these two values here and get 22071, or I can add 293 plus 21778, and that will give me the 22071. So this is the total number of people in the study. Obviously, this was a massive study. Now, the next thing you want to do then is compute these expected frequencies under the null hypothesis is true. So you go to the formula sheet and you see the formula here for the expected values, row tote times column tote divided by grand tote. So to get the 146.48, I multiplied 11,034 times 293 divided by 22071. So that's row total times column total divided by grand total. So here you can see the computations right here. I'm going to pull up my calculator and show you those specifically. So again, we take 11,034. I'm going to multiply that by 293. That gives us this massive number. We're going to divide that by the grand tote, 22071. And there you have it, 146.48. So that's where I get the 146.48. Now what about this expected value here? Again, I take the row total, that's in row number 1, so 11,034. Now I'm going to multiply by the column total, which is here, 21778. That gives me a massive number here, and I divide that by the grand total, 22071, and that gives me the 10887.52. And then similarly, I'd go to this cell here and take the row tote times the column tote divided by the grand tote, and that gives you the 146.52. And then for this cell, the same thing, 11,037 times 21778 divided by 22071, and that gives you that massive number there. And here you can see all the specific computations again. Very straightforward math. Just get your row totes and your column totes and the grand total and just work through it one at a time. Now, another quick check if you want. You can add these four numbers, these new expected values in parentheses here, and it will equal 22071. Because what you've done here is taken the 22,071 men and you've redistributed them across the table here according to the null hypothesis. So if the null hypothesis is true, this is the number of men you should see in each of these cells. So again, a quick computational check is if you add up these numbers in the parentheses, they should add up to the grand total. Okay, so we have the expected cell frequencies. Now we can go on and plug and chug through the chi-square observed formula. So it's observed minus expected squared over expected. So for each cell, I take the observed minus the expected and square that and divide by the expected. So if you go back and look at your table, you'll see all of the numbers here just plugged in. You work through each of these. So this first computation here is 12.34. This one here, you'll get 0.17. This one, you'll get 12.34 again. And this one here, you'll get 0.17. You add these four numbers up and you get 25.02. Here is the chi-square crit, 3.84. We got 25.02. We are in the rejection region. So we reject the null hypothesis, and means the result is statistically significant. And we're going to conclude the first alternative. The data are in the right direction. Now, one thing you can do real quick is to help determine the direction of effect is turn the head counts into percentages. So this 0.86%, where I got that was, I took the number of men in the first cell, which is 189, and I divided that by the grand total, which is 22071, and then multiply that by 100 to get a percentage, and there you get the 0.86. Same thing for the second cell here. I got 0.47%, and then these two percentages here. So what this helps you to understand is, okay, the placebo, it was a slightly higher percentage of men who had a fatal heart attack compared to the aspirin, 0.86 versus 0.7. So there's a direction there. The direction of the effect is in favor of the aspirin. Fewer men are having the fatal heart attack with the aspirin, and then vice versa over here with the non-fatal heart attack. So this tells us the direction of the effect. It's in the expected direction. The aspirin is lowering the incidence of the fatal heart attack. So it appears that then, consistent with expectation, those in the population who consume aspirin will have a lower incidence of recurring heart attack than those who consume a placebo. So this is our standard write-up. It appears that we hedge it because this could be a type 1 or type 3 error. Those in the population, we use that word, and then we get the direction of the effect. Now, if you want to get the P observed, you can go to this website here. So I'll go there real quick and plug in our 25.02 with 1 degrees of freedom and see what happens. So here's the chi-square calculator. We had 1 degree of freedom and 25.02. And it turns out to give us a 0. Now, you cannot have a p-value of exactly 0. What this means is it's less than 1 out of 16 decimals. So it's a very, very tiny p-value. So what we'll do is just report it as p less than 0.001. So you can see how I have it reported as p less than 0.001, which again is less than 0.05. Just another way of saying that, yes, it's statistically significant. This is a highly unusual result given all the assumptions that were made. Now we go to the effect size, and that's Kramer's V. So you go to your handout, you'll find the formula here, chi-square observed over n times k smallest minus 1. K smallest is the number of rows or number of columns, whichever of those is smallest. In this case, there are 2 rows and 2 columns, so it doesn't matter. So it's just 2. So 2 minus 1 here. You plug and chug through. Now chi-square is chi-square. You don't square that value again. It's 25.02 divided by 22071 times 1, and take the square root of that, and you're only going to get 0.03. So this is a near zero effect, as Kramer's V ranges from only 0 to 1. I don't have any Cohen's conventions for Kramer's V, but this is obviously a very small effect size. So if the aspirin is working in the population, it doesn't appear to be a very large effect, at least using Kramer's V. Now, in class, I'm going to talk about the odds ratio and confidence intervals, and we'll get another index of effect size that's more popular than this Kramer's V, and that might tell a little different story. So we'll look at this a little more closely in class. But go ahead and copy all these notes into your, or copy all these slides into your notes, and bring those into class for some points on Monday.